Welcome to everyone, my name is Covi from University of Trento, and today I want to talk to you about numerical experimental analysis of a braced steel frame subjected to fire following earthquake. In this presentation I will introduce briefly the concept of fire following earthquake, the EQUFIRE project, the concept of hybrid testing, the experimental results, and the model calibration performed using SAFIR and OPENSEES. Fires following earthquake have produced historically large post-earthquake damage and losses in terms of life, building and economical cost. Here you can see some example of fire after an earthquake. It is possible to indicate the earthquake of San Francisco in 1906 as the first of a series of earthquakes where the developing of the fire caused more damage than the seismic event. I have been primarily involved in different aspects related to the EQUFIRE project that aims to provide experimental data to study the response of structure and non-structural components and the interaction with different fire protection systems to scenario of fire following earthquake. In particular, a 4-story 3-bay steel frame with concentric bracing in the central bay was selected for the experimental test campaign. This frame is a part of an office building with a square plane of 12.5 meters and it is located in Lisbon, in Portugal, in an area of medium-high seismicity. The story height is 3 meters, with exception of the first floor, which is 3.6 meters height, so that it can be tested at the full scale in the laboratory. The columns are continuous and all connections are regarded as pinned. Two different steel grades were used, namely S275 for the braces and S355 for beams and columns. The steel profiles composing the bracing system were oriented according to the weak axis in the plane of the frame. Different hybrid fire following earthquake tests of the frame in two different laboratories were performed, one using single columns subjected to fire following earthquake at the furnace of the Federal Institute for Materials Research and Testing BAM in Berlin, that I will present today, and a seismic pseudodynamic test of the real scale 1-story frame at the European laboratory JRC. The concept of hybrid test is very simple. In fact, we can physically build only the part that we want to study or some element that it's difficult to simulate its behavior, and all the other part we can reproduce into a simulation in a real-time computer with different technique. The experimental tests at BAM were performed using a substructure technique in which the physical column was first subjected to the horizontal and vertical displacement time history computed to a numerical simulation. Then the column was heated by the ISO 8034 standard heating curve, and a constant numerical axial stiffness representative of the surrounding structure was applied as a boundary condition at the top of the physical column. In this slide you can see a general view of the fire engineering laboratory at BAM located in Berlin, and the view of the control room of the laboratory and the vertical furnace used during the test campaign. 5 fire following earthquake tests were conducted at BAM. The first 2 tests regard the columns without fire protection elements, and in this and the following slide you can see some pictures taken before, during and after the test of each column. In the second test, we tested the column with the fire protection board system, namely Promatec H, and the reinforced joints that are used to connect the boards, designed for seismic region. The thickness of the boards is 20 mm. In the third test, we tested the column with the same fire protection of previous slide, but this time with normal joints. And also in this slide you can see other information about the thermal properties of the boards. In the last test, we tested the column with the fire protection system, namely Promospray P300, that is a gypsum-based wet mix spray apply fire-resistant material designed for application in seismic regions in which a mechanical reinforcing mesh was placed in the middle of the applied material. The columns were instrumented with 6 thermocouples per section, 4 for the flanges and 2 for the whips, in 3 sections along the height of the column. Other 2 additional thermocouples were placed on the end of the plates. 15 accelerogram were selected considering the type of spectrum, earthquake scenario, local site condition, period range and ground motion components using the European Strong Motion database. The oscillograms were modified to match the target spectrum in the period range between 0.4 and 0.9 seconds that include the fundamental period of the structure. Among the 15 oscillograms, the one shown in this slide was selected for the experimental hybrid test and the numerical analysis based on the three main requirements. The selected oscillogram had to cause some damage to the bracing elements. The horizontal displacement of the first floor had to be equal or lower 10 plus minus 30 mm to be compatible with the stroke of the horizontal actuator inside the BAM furnace, and the axial force of the interior column at the base of the second floor had to be below 1000 kN to be compatible with the actuators to impose two vertical loads on the specimen at the JRC line. This animation shows the comparison between the numerical model developed before the test and the experimental test of the unprotected columns, column A and column E, during the seismic test before the fire. In detail, in the upper left part, you can see the deformed shape of the numerical model. At the bottom left corner, you can see the acceleration. On the right, you can see the horizontal displacement and the axial displacement and the axial force. In this other animation, you can see the comparison between the numerical model, as before, developed before the test, and the experimental test of one column with a gypsum board during the seismic test, before the fire event. On the top right, you can see the video time-lapse of the column inside the furnace during the seismic event, and in the bottom right, you can see the horizontal displacement of the column. This slide shows the comparison of the results of the seismic test and of the numerical simulation in terms of the horizontal displacement, axial displacement, and axial force for all tested columns. There is a little difference in negative axial displacements and forces because the vertical actuator of the furnace cannot apply tension forces to the specimen. The axial stiffness was numerically estimated by a static nonlinear analysis. In detail, the full structure was subjected to the gravity loads and to the selected oscillogram through a nonlinear time history analysis. Then the physical columns was removed and the frame was constrained at each floor to reproduce the boundary condition of the actual experimental setup at BAM. Finally, a monotonic displacement control pattern, which continuously increases, was performed. I showed in this slide that the equivalent stiffness is neither constant nor linear. Due to this reason, it was not possible to exactly reproduce the same axial force condition in the column during the test using a constant value. However, the value of K was chosen to reach a similar critical temperature. In order to determine a more appropriate constant equivalent axial stiffness value, this slide shows the results in terms of the axial force and vertical displacement compared with the numerical analysis conducted on the full structure. As it is possible to observe, a good value of the equivalent stiffness of the surrounding structure after the damage caused by the earthquake is equal to 5.3, and this value was used in all the tests. The comparison of the test of the unprotected column E and the numerical model before the calibration is presented in this animation. At the top left there is a video time-lapse of the test, at the bottom left the mean of the temperature recorded by the thermocouples, at the top right you can see the shape deformation of the numerical model, and at the bottom right you can see the axial displacement and axial force. This slide presents the comparison of the fire-following earthquake test on the specimens with the three fire protection. Test number 2 on column B was interrupted due to a malfunction of a component and then was restarted. The specimens with the two different type fire protection board system, column B and column C, showed a similar performance. The gypsum-based spray material delayed the development of the temperature in column D with respect of columns B and C. As shown in this slide, cracks on the fire protection elements developed due to the combination of seismic and fire actions. However, those cracks were not large enough to compromise the fire resistance of the columns. This was mainly due to the fact that the energy dissipation and damage caused by the earthquake is localized in the diagonals of the bracing system and not in the column, and to the limit of the horizontal displacement that can be applied in the laboratory, that is plus minus 30 mm. Two advanced finite element models that are more representative of the experimental test were created for the calibration. A 3D finite element model of the column inside the furnace using OPENSEES, 50 nonlinear beam elements based on the correlational formulation and the constitutive law provided by Eurocode 3 part 2 was adopted to model the mechanical properties of steel at elevated temperature. Other two 3D finite element models of the column inside the furnace using SAFIR were created. One model was created using beam elements and the other one using shell elements. The calibration of the numerical models consists in three different aspects to be considered: a rotational stiffness based on the actual type of joint, a more representative temperature distribution, and the real load state after the earthquake event measured in the laboratory. This slide shows the comparison of the experimental and numerical before and after the calibration result using OPENSEES for the fire following earthquake test on the column A and E without fire protection, in terms of the evolution of the mean temperature, axial displacement, and axial force. The comparison after calibration demonstrates good agreement. Here you can see the results of different models developed in SAFIR, starting from the unprotected column A. In detail, the blue curves refer to the beam and shell model without taking into account any axial and rotational springs. The green curves are the results with the axial spring value to simulate the stiffness of the rest part of the structure, and the red curves show the result with taking into account the rotational stiffness of the base and top connection. Here you can see the numerical calibration results of the column C as an example of the fireball protection system, in terms of axial displacement, axial stiffness, and axial forces. In this other slide you can see the numerical calibration result of the column D with gypsum-based sprayed protection system. The comparison between the numerical analysis and the experimental results for the columns demonstrated a good agreement for both seismic and fire actions. No serious damage was observed that would undermine the fire resistance of the columns. A more significant damage to the fire protection of the dissipative elements bracing system is expected during the fire following earthquake test series at the JRC laboratory. Thank you for your attention.